Now I will be looking at a general category of optimization problems known as constraint optimization problems. So for this for this type of optimization problems, we will use a certain method that I would like to describe next. But first, what type of problems are constraint optimization problems? So basically the general optimization problem looks like this. So we maximize a certain objective function, and now the additional thing, the constraint, will end up being subject to a certain constraint. Constraint 1. So you might have multiple constraints, right? So constraint 2 and so on. Constraint n. So you might have n constraints, for example, right? So this is the objective function. Objective function that you want to optimize. You have some certain control variables, x, y, z, you name it, or we can call it x1 through xm, for instance, and we have those x's should satisfy certain constraints. So this is a standard constraint optimization problem for which the solution follows directly by something called Lagrangian. So we would go ahead and construct the Lagrangian of each problem, optimization problem, and the idea is extremely simple. You just write Lagrangian as a combination of the objective function. So you have the objective function plus, for each constraint we create a penalty variable, so lambda 1, for instance, a parameter, and we have the constraint 1 here, constraint 1 plus lambda 2 times constraint 2, and so on. In our case, we have, say, n different constraints, so constraint n. So once you have these the Lagrangian, the next step is to write out the first order conditions or first order necessary conditions, which are basically that you need to take the derivative of the Lagrangian with respect to each variable independently and set each one of them equal to 0, right? So this is equal to 0 for all I. So this is a partial derivative for each and every single variable. You just set that derivative equal to 0 for all I, and in our case we have m variable, so I equals from 1 to m, and besides we still have the actual constraints, which are pretty good. So we will end up with n constraints, which will give us n equations, and besides we will have m conditions coming from these. So in total we will end up with n plus m equations. So we effectively turned an optimization problem into a system of equations. With how many equations? N equations here, the constraints basically, and then m equations here. Each one is setting equal to 0. We'll have, so m plus n equations. That's it. That's the rest of the problem is to solve a system of equations, which you have done it since, I guess, 6th or 7th grade in middle school. Awesome. So what are some examples to constraint optimization? There's an abundance. I mean, almost in every discipline you can imagine, there's always an optimization problem behind the screen. So what we have is here in the first example, here is the example from economics, the utility maximization problem of the consumer. At the end of that maximization problem, once the consumer solves this, that will tell the consumer his choices. So if the consumer derives utility, pleasure, from consuming, say, two goods, X and Y, so we can try to maximize that objective function U, subject to the individual's budget constraint. So this is the individual's budget. So as long as you are within your budget, in this example I, your income, you should be fine, where PX here represents the price of good X. X itself represents the quantity consumed of good X, plus P sub Y is the price of good Y, and Y itself represents the quantity consumed of good Y. Alright, so here is the output maximization problem, another example from economics. We want to maximize our output, the production in a facility, in a firm, subject to a constraint that the cost should not exceed a certain threshold. That's it. Here R represents the price of capital and W represents the price of labor. This is very much similar to what we just did in the previous utility maximization problem, where Px and Py are the prices of individual goods, X and Y. Here's another example. This is a cost minimization example, again from economics. This time, instead of maximizing output given a certain cost, this time we want to minimize the cost given a certain output level. And again, this is obviously a constraint optimization, because in each case there's an objective function, in this case for instance this one, and some constraints subject to the constraints. Just as an example, sometimes in economics profession it is, well, not sometimes, almost all the time, it is common practice to have capital and labor on the x and y axes, and then to draw the for instance, let's have a look at the cost minimization problem. So we can draw what's called as the isoquant. So this is the isoquant associated with this level of production. So we want to produce Q equals Q bar. This is the minimum level that we want to produce. So if you want to produce this much, what should be the cost? What combination of capital and labor should you use? Well, depends on the relative prices of capital and labor. If capital is relatively inexpensive, we have cost curves like this. All we do is cost curve values will be lower and lower as we approach the origin, and ultimately it will become the minimal at that point. So this is the cost, the level cost, which will minimize the overall cost, and we will still be able to produce the same goods. What should be the combination of capital and labor that we should be using? These are the combination K star and L star. Well, this is when prices are the way they are, so the cost curves are like this. What if the relative prices of machines and labor have changed? Suppose that this is now the new relative prices. So as we shift these lines, you guys can see a tangency value. So this is the new combination of capital and labor if prices were to change, and as a result our decision would change. For instance, in this example, it seems we are bound to use less capital and more labor, simply because labor is becoming cheaper relative to capital. This theory is very important. Just as an example, suppose that these red and blue lines are actual real lines for the production process that, say, for instance, Toyota. It's a automobile maker, right? Toyota. It's a Japanese car maker. It has factories in Japan and in the United States. It turns out that these are the cost functions of Toyota for its factories in Japan, versus the same car maker has different cost curves in the US. So when you look at these cost curves, you suddenly realize that it turns out that capital is cheaper in Japan and labor is cheaper in the US. So labor in Japan is more expensive, capital in the US is more expensive. If that's the case, of course it makes more sense, because labor is so expensive in Japan. In their production process, when they want to produce the same amount of output, they use more capital and less labor compared to the US, where in the US, if we were to produce the same number of output cars, in this case it is this you guys can clearly see this isoquant. This is the isoquant associated with this much production. And clearly in the same car maker in the US makes use of less machines and more labor, hires more workers, American workers. Why? It's because even though it's the same company, it has access to the same types of technologies, but in the end, what is the relative prices, right? So when you compare labor, the wages in the US versus wages in Japan, Japanese wages are significantly higher than US wages. However, rental rate of capital in Japan is cheaper than rental rate of capital in the US. So it makes no surprise as a result, because Japanese workforce is more expensive, the amount of labor that goes into the production in the US is higher than in Japan, right? So this is related to US and this is Japan. But this is quite the opposite for the capital. For the capital, it is that K star in Japan, the Japanese factories, they use more capital and than their counterparts in the US, and even for manufacturing the very same automobile. All right, so hopefully this is useful. All of this information can easily be gathered from these equations, basically. Very straightforward. All you do is just construct the Lagrangian, just we did in our videos. And so that's it. So once you construct the Lagrangian, take the partial derivative, set them equal to 0. The optimization problem automatically is converted into a system of equations with m plus n equations, regardless of the number of equations. Obviously, since elementary school, we know how to solve a system of, say, for instance, 2 equations and 2 unknowns. It's pretty much the same techniques to solve 3 equations and 3 unknowns, or 4 equations and 4 unknowns. It should be very straightforward. Just as a reminder, for instance, if you were to solve this system of equations, that would be 2 equations and 2 unknowns. X plus 3y is equal to 12. Oops, that's a 2. Question is, what is the value of x and y? This is decidedly a simple problem. And we can use the standard algebraic techniques to solve this problem. Now, again, to summarize, the constraint optimization problem is converted into a system of equations by just using this idea of a Lagrangian. Take the derivative of the Lagrangian m times, like whatever is the number of variables, take the derivative of that Lagrangian with respect to every single one of these variables, and then you still have the initial n constraints. So m equations from the derivatives, n equations from the constraints. The total will give you a system of m plus n equations for which you can easily solve it for the control variables xi's, basically. That's very straightforward. Awesome. So another example. Our next example is from the discipline of finance. In finance, this is the standard portfolio optimization problem. Here we try to minimize risk subject to a certain return. A return constraint. So if you serve as a portfolio manager and you have your clients, you give your clients the following information. So from this portfolio optimization, usually when you solve this, what comes out is a curve. And based on that curve, suppose that we put risk on the x-axis and return on the y-axis. As a financial advisor, one idea is the following. You can tell your client, tell me how much return you would like to make on your investment, and I can tell you exactly the minimum risk that you will have to take if you want to earn that return, basically. So that's straightforward. So this is the minimum risk that you should be taking if you would like to earn a certain minimum amount of return. Alternatively, you can, so in a sense, it's as if any of these allocations are good, but obviously attainable. So anything inside this region is attainable. Obviously, you want to minimize the value, which is this one. Alternatively, what you can do is you can tell your risk preference. You can tell that you don't want to take a risk higher than this. This is the maximum risk you are willing to take. This is a reinterpretation of the same problem. In that case, what is the maximum amount of return that you can obtain? Again, going up, it will be right here. So that would be a maximum return. So it depends on what is the framework you're analyzing. In this example here, we are minimizing risk subject to a return. So that would be the first interpretation. An alternative would be to flip this with that. Right? So the objective function with the constraints, once you flip them, so the new problem becomes maximizing return subject to risk, a certain risk level, not being higher than a threshold, and that will give us the very same answer. So these problems are referred to as duals. All right. Next problem is an example from linear optimization, linear programming. This is a standard type of equations from operations management field. If you have a linear objective function and some number of constraints. It doesn't have to be like 2, it can be any number of constraints. Then how do you solve this? There are multiple ways to solve it. We did already some examples using Microsoft Excel's solver function, which already have a built-in simplex LP algorithm. It's very straightforward to solve these problems like this. Just be aware that these type of problems in general create corner solutions, right? So because these are linear problems. At the time, the famous algorithm to solve this were the simplex, right? So simplex algorithm. This is a very when I was in grad school many years ago, about 20 years ago, this is the algorithm that they made us memorize. It was a very tricky algorithm, but machines today, they do it for free, right? It's very straightforward. So when I said because it's a linear programming problem, why is it linear programming? Because the objective function is a linear function in terms of the variables we have, and the constraints are also linear. This is a standard linear programming problem. The solutions usually will end up being kinks, right? So for instance, suppose that we have two variables, x1 and x2 only. So I'm just dropping the third ones. All right, so just drop these. So what's going to happen is we want to maximize our objective, which is given by this a1x1 plus a2x2. When you draw it, suppose that it comes out like this. So this is a1x1 plus a2x2, and this is set equal to, say, x bar, for instance. You can change the value of x bar, so they will be parallel shifts along here. So if you are given a certain these equations, constraints, suppose that the constraints are such that this is the shape of your constraints. It now makes sense that this is your budget, in a sense, right? So this is the feasible allocations. Given any of these feasible allocations, the one which will give you the highest, which will maximize the value of the objective function is, as you go northeast, your objective function gets a higher and higher value. Oops, let me just make sure this looks like a straight line, right? It was intended to be a straight line. So clearly the point where the further we can push that line, those blue lines, is that point here, and that's our choice. So at this level of x1 star, we can call it, and at this level of x2 star, this is what will make this objective function maximize. That will maximize that objective function. So that will be the choice variable. The outcome. Yeah, so that's kind of like a good summary of what we're going to cover related to this topic of optimization. There's a lot of different types of optimization problems. For instance, just for the record, the portfolio optimization problem that we described here is usually referred to as a quadratic optimization problem, because as you guys can see, the objective function, the risk here, this symbol, these are all matrix symbols here for the portfolio optimization problem. That thing in the middle is the covariance matrix. The x's here represent the portfolio weights constituting your portfolio. So it's clearly a quadratic, a second degree polynomial in a sense, and as a result, this is a special family of convex optimization problems, which we usually refer to as quadratic optimization. All right, so let me just stop right here.